Good morning, everyone. My name is Jean Tan, and I am an intern engineer for Exemplary Energy, which is a consultancy that analyzes weather and climate data to help improve the understanding of the impact of weather and climate on the performance of buildings, solar PV, and other engineered systems. I am grateful for this opportunity to present at the APSRC 2022 the development of extreme climate data files for design resilience, which is one of the projects I am working on as part of Exemplary Energy's goal to improve our Australian weather and climate data services. Most simulation work in the building industry focuses on evaluating building performance under typical climate conditions, for which the reference meteorological year or RMY data would be used as an input. This only considers the typical expected climate without giving much understanding on how a building would perform over time under variations of the existing climate. And such analysis can benefit from a characterization of extreme climate as an input to the simulations. In a similar way that RMY represents the average and historically expected climate for a typical year, an extreme meteorological year or XMY represents conditions that produce extremely high or low building energy consumption across the entire year. In addition to gaining an understanding of the performance of building energy in extreme years, XMY data can be used by developers of renewable energy generation infrastructure to demonstrate an understanding of the variances likely to be encountered year on year, and hence an understanding of the inherent financial risks of their proposed design. Although this has been widely studied in the development of major infrastructure like solar and wind farms, there is still a lack of consensus in the industry on what extremes mean for buildings. At Exemplary Energy, we have looked at defining XMY for solar PV performance and have produced a dataset that characterizes the climate of a 1st, 10th, 90th, and 99th percentile year of performance for a PV system. This was done using a combination of tools, which include the System Advisor model, our in-house weather data analysis software, and Energy Plus. The 1st, 10th, 90th, and 99th percentile weather files were produced for all 8 Australian climate zones in the National Construction Code, and the results were presented by my successors at the APSRC in 2020 and 2021. We attempted to do the same kind of work for building HVAC, but buildings and HVAC systems are more complex than solar PV systems. Firstly, PV is closely correlated to a single weather element, solar irradiation, and PV systems generally perform quite similarly across the range, whether it's a small rooftop system or a big solar farm. In contrast, buildings and HVAC systems are more diverse. For example, smaller buildings with a lot of glazing may be highly sensitive to variations in horizontal irradiation, while other systems may be more or less sensitive to humidity and dry bulb temperature. We have looked at the validity of applying the XMY dataset developed for solar PV to buildings, and we found, as expected, that the extreme weather data defined in this way is incapable of correctly representing the extremities of energy consumption or demand of a building. The results of our analysis are shown on this slide. In this graph, the historical annual HVAC energy averaged across our 3 building archetypes in Canberra are ranked in increasing order, with the hypothetical XMYs highlighted with colored bars. As you can see, the 90th percentile comes up as low energy use, the 1st percentile is somewhere in the middle, and the 10th percentile is a high energy consumption year for these buildings. This clearly shows that the XMY data sets developed for applications in solar PV modeling are not valid for use on buildings. In developing the XMY datasets for buildings, we used a new technique where we ran the full 30 years of weather history for the location through our building archetypes modeled in Energy Plus to generate the monthly heating and cooling data over that period. We then assess whether the extreme year for one building type is valid across these 3 archetypes by looking for correlation between different building types. We then developed a range of descriptive statistics and then assess whether the results fit a Gaussian distribution, which would mean that we can then apply standard statistical techniques to further analyze the results. This figure here shows the annual energy consumption for each of our 3 building archetypes, and there is some correlation between the 3. This implies that it would be feasible to produce an XMY dataset that is reasonably meaningful across a broad sector of commercial buildings. Stronger correlation is demonstrated between building types when the energy use is considered separately into heating and cooling. And here is an example graph showing the correlation of cooling energy use in Canberra between the mid-rise and high-rise building types. This correlation indicates that the proposed extreme meteorological years would be feasible for most commercial building types, or at least those represented by our 3 building archetypes. One of the benefits of working with a large amount of weather data spanning across a long period of time is observing the trends over time. Here we are looking at the cooling and heating averaged across the 3 building types in Canberra. We can see a significant increase in the cooling load and a decrease in the heating load over the last 30 years, which we are attributing to a warming climate. There is more than 20% increase in the cooling load demand for the same building types from 1990 to the present, and there is a necessity to incorporate the likely future increase in cooling loads due to climate change impact into building energy simulations. This figure shows the annual total HVAC data between 1990 and 2017 for the 3-story building type in Canberra, roughly fitting a bell curve distribution. In this graph, the annual HVAC energy use from each year in history are ranked in ascending order from lowest to highest. Since we are assuming a Gaussian distribution, we are able to calculate the expected probability values of HVAC energy use at the 1st, 10th, 90th, and 99th percentile, which are indicated by the colored bars in this graph. Theoretically, we can select the closest historical year to approximate the desired percentile value, and the corresponding years to each p-value are listed on the right here. So for this dataset, the closest year in history to the 99th percentile is 1996, which is at the 98.8 percentile. And the closest to the 10th percentile is the year 2015, which is at the 12.7th percentile. We believe we can improve on this. We are looking at developing a statistical technique similar to the production of the reference meteorological year data, which is to select a series of 12 historical months to create an artificial year that is representative of the 1st, 10th, 90th, and 99th percentile years. We expect to offer an XMY dataset for a number of key locations across Australia in early 2023 using this technique. A further goal is to generalize the technique using multivariate statistical correlation to evaluate the statistical relationships between the weather elements and the extremities of energy demand. This will allow us to develop a method to bypass the multi-year simulation for the specific location, which will then enable us to provide an XMY dataset for any application for any of the 250 locations we are tracking in Australia. This will initially be a manual process, and we plan to start with the key capital cities to cover the 8 National Construction Code climate zones, and then move on from there. That brings us to the end of my presentation. Thank you for your attention. Unfortunately, due to unforeseen circumstances, we are not able to have a live Q&A session, but please do reach us by email at this address with your questions, feedback, or comments. Thank you.